Hello guys, I'm Gautham Thejur back here again after long days. How are you all guys doing? Are you all fine? I hope you're fine. Okay, the main purpose of this video is today I'm gonna make you understand what is a Magnus effect, which is a cool physics topic. Okay, many of you may have seen the Magnus effect in your daily life, but you didn't understand that it was a Magnus effect. It's not your fault, because it's only because you didn't you're ignorant to that. That's it. Okay. And some of you may have searched what is a Magnus effect and ran into my video and chose my video, and you're right now seeing my video, right? Okay, then for you guys I'm telling something. You will have a clear-cut idea after leaving this video. After seeing this video, you will have a clear-cut idea that what is a Magnus effect. Just imagine what I say. A person standing on top of a building is throwing a ball like this. Let me show you so that you can get a clear-cut idea. And this is a man, and he is throwing his ball. Okay, let it be a vertical direction. It's better. Okay, this is the direction that the ball is moving. Ball is moving in this direction. But this is the kind of path that most of you are expecting it should go, right? But here what happened is something different. It didn't happen in the way that it should. It had, oh wait a sec. The ball on moving just deviated its path, and it should reach towards the ground, right? But it didn't reach the ground. It just deviated its path and struck the building. But why did that happen? I was also dubious on saying or on finding this question, and now I have a particular answer to that. And the question is a very nice question, this question. And the reason behind this is our topic. It's nothing other than the Magnus effect. But why did this happen? This ball, why did it deviate towards the building? And after before leaving this video, you will have a nice idea why did this happen. Okay, let's move into the topic. This is it. Let this ball be rotating in a clockwise direction. Clockwise direction is this, right? So this ball is rotating in a clockwise direction. Okay, this ball is rotating in a clockwise direction. Okay, and this ball from its center is having a translational motion like this towards that direction. This ball is falling towards the ground, okay? And for your better understanding, I'm drawing like this. I have drawn like this, okay? Now, I'm going to take a point particle at here and here of this ball, and this is it, the direction of the velocities. Got it? And this is the velocity of that point particle as it's tangentially. The velocities in a circle or rotational motion is always tangents, right? Tangentially drawn. Okay. Now these are the velocities. Okay, man. Now let me ask you something. The velocity, the movement of the air currents are in this path, this direction, right? These directions. But this velocity, is in opposite direction. This point particle executes a velocity in opposite direction to the air current's direction, right? And that's it. There lies our problem. We all know that two velocities, that's not going to be possible in different directions. So here comes our answer. The body on rotating executes a circular motion, right? And velocity is in opposite direction. So velocity lowers lowers at the topmost point. Velocity at this point, I'm gonna call this point as A and this point as B, okay, for better understanding. And the velocity at topmost point, velocity at A, is always less than velocity at B position, right? And now, as you always know, many of you may have studied the Bernoulli's equation or Bernoulli's theorem mainly. Bernoulli's theorem mainly says that when velocity increases, pressure decreases, right? So that's it. When velocity at position A increases, the pressure at position A always decreases than pressure at position B. That's it, guys. This point has less pressure and this point has greater pressure than this point, right? And that's the reason. Now we are coming to the conclusion. As this body is, ball is rotating in clockwise direction and the air currents are moving in this direction, so the pressure of air will always move from high pressure to low pressure, right? That is being said in Bernoulli's equation. Alright, okay. And so as the velocity at this position is lesser than this position, the ball feels a higher pressure of air currents from this side, this A side, towards this side. Got it? So the ball will feel a velocity towards this side. Got it? Now that is the reason why the ball will execute a projectile motion like this after that. It will not go in this direction, but it will execute a motion like this. So that is why it bends. Now guys, I'm going to summarize this a little bit shortly. A ball is moving in this direction with a velocity, and we are drawing the tangent velocities at this point particles, for this point particles, and the translation motion creates such a velocity in that direction. And so the air currents are moving towards its opposite directions with respect to the ball, right? And so the velocity at point A is less than velocity at point B. It's because the velocity of this point particle is always in opposite direction to the velocity of the air currents. So it will create lesser. That is the net of velocity. The velocity at point A will always be less than velocity of B. That creates a pressure at point A will always be lesser than pressure at point B. Sorry guys, I had done a mistake here. I think you might have noticed, as I always say, firstly itself I said that pressure is inversely proportional to velocity with respect to Bernoulli's equation. Sorry. I'm really sorry. So pressure at point A is greater than pressure at point B. So that is why the air currents at this point will make the ball move towards this side. Because the pressure at point A is greater than pressure at point B, it will make this point, the air currents at this position have a greater pressure. So as the natural law is that everything must move from higher concentration to lower concentration, right? That's a that's a common sense, right? Common logic. Okay, so the pressure at point A is greater than point B, so the air currents will make this ball move from this side to this side because the pressure at point A is greater than pressure at point B. Okay guys, and that makes a projectile motion like this. And you can see the applications for this when you watch the cricket guy. You can see, or you can get better examples from cricket match. As you always see, the spins, the backspin, the off spin, and many such kind of throwing balls, right? Those all have a thing behind that called as a Magnus effect. This Magnus effect is nothing but it's taken from the Bernoulli's equation. Magnus force is the force exerted on a rapidly spinning cylinder or sphere moving through air or another fluid in a direction at an angle to the axis of spin following the Bernoulli's relation. This force is responsible for the serving of balls when hit or thrown with spin. This effect is called as Magnus effect, guys. It's such interesting, right? It was interesting to me. I don't know about you guys. Magnus effect is a particular manifestation of Bernoulli's equation or Bernoulli's theorem. Bernoulli's theorem. As it always says, Bernoulli's theorem says that the fluid pressure decreases at points where the speed of the fluid increases, right? So that is being said here. This is that thing that I told you right now. In the case of a ball spinning through the air, the turning ball drags some of the air around with it, and that's the reason for spins that you see in a cricket match. Everything has science, guys. Just try to figure it out. You will be amazed. I always like to do that. And that's it. That's all about Magnus effect. I think you guys have a clear idea what is the Magnus effect. The air currents at points A feels greater velocity at A because of the velocity of the ball. Ball at this point particle have a velocity towards that direction, and the velocity of the air currents is towards this direction. So velocity at point A is less than velocity at the point B because it's always the velocity of the ball and the velocity of the air currents are towards the same direction. So it creates a higher velocity at this position. Here creates a lesser velocity and here creates a higher velocity, and so it makes the pressure at this position greater than pressure at this position. So as the air always move from high pressure to low pressure, it will move from moving from high pressure to lower pressure makes the ball move in this direction, and it will execute such a motion. And that's the reason, or that's the Magnus effect. Okay guys, see you later with another wonderful, fantastic, fantabulous physics topic. Till then, goodbye.